I'd like to revisit conservation of energy and see if there's anything that we missed when we talked about it initially. So we have the ball here, and we're going to drop the ball. It's going to roll down the ramp, and this photo gate timer will measure the time it takes to go a certain distance. And in the past, we said that the change in the gravitational potential energy should equal the kinetic energy of the ball at the bottom. That is to say, if we were to let go of the ball here and it drops lower and lower and lower, losing gravitational potential, it goes faster and faster and faster, gaining kinetic energy. And if we knew the mass and the acceleration of gravity and the change in height, it should equal 1/2 the mass of that ball times its velocity squared. So we're going to see if that's actually true. This device here has a little electric eye, an invisible beam of light using infrared that goes between here and here. And when the ball breaks that beam of light, it starts the timer. And then there's another beam of light back here, and when it goes through that, it stops the timer. So we can use a meter stick to figure out how high the ball initially started, 10, 20, 30, 40, 45.1 centimeters, or 0.451 meters is how far the ball is going to drop, our change in height. And the timer read 0.0592 seconds. We measured the time to within a tenth, a hundredth, a thousandth, to within 10,000ths of a second that it took to go this distance. And it really is from center to center, because that's where the electric eyes are. So from center to center, but it'd be the same distance if I just scoot that over and say the trailing edge to the trailing edge. So that the distance the ball went was 0.125 meters in this amount of time. So let's see if all these numbers work out. The change in gravitational potential should equal the kinetic energy. So we see the mass cancels out. And if I multiply both sides by 2 and then take the square root, I can find out the velocity of that ball, what it should be. Okay, so I know the acceleration of gravity, I know the height, and it should be going 2.97 meters per second by the time it gets down here and has lost all that gravitational potential. Well, let's measure what it actually was doing. So velocity is distance divided by time, that distance divided by this time. It is actually going considerably slower than we said it should have been going. Yikes. We might need to know a little bit more about conservation of energy. Well, let's check it out in terms of energy. The gravitational potential, mg delta y, says we need to know the mass. So I put the ball on the scale and it has a mass of 67.1 grams, 0.0671 kilograms. So mass, gravity, and change in height. This lost 0.297 joules of energy in dropping this height. Well, let's see how much kinetic energy it had. 1/2 mass times velocity squared. It only had 0.150 joules of kinetic energy. This is how much potential energy it lost, but it only gained that much kinetic energy. There's just this number here is a little less than half that number. A little less than half of the energy that we found it had is missing. We didn't account for it. So what type of energy did that ball also have? Well, let's remind ourselves what translational kinetic energy is. We just called it kinetic energy in the past. We didn't have to call it translational kinetic energy because we didn't know there were two kinds of kinetic energy. And we used that to solve problems where we said that how fast is a roller coaster going to be going down here? We said all the gravitational potential was transformed into kinetic energy, but now we know it's translational kinetic energy. So that ball, if it's just moving along like that, with some mass and some velocity, we can calculate its kinetic energy. But was the ball just moving like that? Or was it moving in a rotational sense as well? Okay, that ball was rotating quite fast, I might add. And that is another form of kinetic energy. We're going to call it rotational kinetic energy. And we can probably guess at the equation for rotational kinetic energy. It's going to be very similar to our translational kinetic energy, but we just got to be a little more careful. We can't just plug in how much mass it has or how fast it's traveling in a line. We have to do it in the rotational sense. So we have to calculate how much rotational inertia it has, based upon whether it's a sphere, a ring, a disc, a stick, or anything like that. And then how much mass it has and its radius. And then it's not its tangential velocity that matters, it's its angular velocity. It's how fast it's spinning. All right, so that's our equation for rotational kinetic energy. Now, were we like totally off base when we said the roller coaster up here was transformed, the potential energy here was transformed to kinetic energy there? Well, it worked out pretty well in the past because a roller coaster is mostly translational kinetic energy. All this mass of the people and the seats and the structure is just moving in a line. Very little of its energy was in things that were rotating, like these wheels. So we weren't too far off base saying that potential energy up there was transformed into translational kinetic energy down there. But when the entire thing is rotating, then we got to be a little more careful. So let's do this problem again, but realize that the gravitational potential changed into two kinds of kinetic energy, a translational kinetic energy and a rotational kinetic energy. So mg delta y is going to equal 1/2 mv squared, and then we're adding now also onto that the rotational kinetic energy. And what I want to do here is I want to solve this problem for the velocity, figure out how fast it should have been going in comparison to how fast it really was going. Well, the problem is we got to get these two things into units of mass and velocity. So these are our standard ways of converting from an angular concept to a tangential concept. The angle in radians times radius would be the length of the arc. An angular velocity times the radius would be the tangential velocity. And an angular acceleration times the radius would be a tangential acceleration. So we're going to use this one right here to convert angular velocity into a tangential velocity. And because it is a sphere, the rotational inertia of a sphere is 2/5 mass times radius squared. So we're going to go ahead and substitute in, this is the rotational inertia of our sphere, and then this would be its angular velocity, which is the tangential divided by the radius, same thing as its angular. So I'm going to go ahead and square each of those. The mass does cancel. So when I square each of those, I'm left with this radius squared and this radius squared. One's in the numerator, one's in the denominator, and you would think, oh, I can cancel those. And to be honest with you, when I went through this problem the first time, I canceled them and then realized later that they're not the same radius. What? So we have to be a little careful. This is the radius that's going to affect how much rotational inertia it has, and it has a different radius that affects how fast it's traveling angularly. Let me explain. So that ball is resting on two rails here. And so this is the center of that ball. This is the axis for which it is rotating. And this is where it's touching the rails. So the distance from its axis of rotation to where it's touching, that's going to be its tangential velocity based upon how far it is where it's touching the rails. But the distance from the center to the outside is the radius we're going to use to calculate how much rotational inertia it has. Let's think of it this way. If these rails were further apart and one rail was touching like up in here and the other was touching over there, this thing would be like spinning really, really fast, but moving along tangentially pretty slow because it's on such a small radius there. So we do really have to be careful with those. And let's go ahead and calculate what each of them are. These are vernier calipers, and you can use it to measure the diameter of the ball. It's not very intuitive how to use vernier calipers, so reading that can be a little challenging. And if you don't know how to do that, I do have a video on that called Measurement. It's one of the first videos in my playlists. So looking at that, it is 2.54 centimeters. We might recognize that as 1 inch. This ball is just 1 inch in diameter. Okay, so from there to there, that means the radius is half of that. So this is 0.127 and this is 0.127. And then I can also use this other feature. Instead of measuring the outside, we can touch with these two things and measure an inside distance. So when I zoom in on that right there, that is 1.55 centimeters. And again, if you look at that and think, I don't know how he got that, look at my video on measurement. So the distance between here and here is 1.55 centimeters. This distance right here is going to be half of that. So we have this triangle, and we can use Pythagorean's theorem to find out what this radius is. So this radius is 1.01 centimeters when the overall radius is 1.27. You can see they're very different numbers, and we really did have to calculate what this radius was to figure out how fast its tangential velocity is. So we'll come back to here now. The radius that calculates its inertia, rotational inertia, is this, and the radius that determines its angular velocity was this. So there is a v squared in this term and a v squared in that term. I'm going to factor that out. I'm still left with a 1/2. I'm still left with the 2/10. I'm still left with that and that. And it does get a little ugly, but we can do algebra, and we can do it very carefully. All I'm going to do is I want to get this by itself. I'm going to divide that whole term by both sides, or both sides by that whole term. It's going to show up in the denominator here. I'm left with v squared, so then I just take the square root. Okay, so it would get a little messy if I showed all that, but that's the number we would come up with if we plug those numbers in. So we get better. Before it was 2.97, and now we're at 2.32, still a lot closer to there, but not quite as close as I would like. Let's look at the energies here. So based upon the mass and gravity and how much it changed its height, mass, gravity, change in height, it should have lost 0.297 joules of potential energy. And then that was transformed into a translational kinetic energy, and it had this much translational kinetic energy. The rotational kinetic energy was that, and we can calculate its rotational inertia, and we can calculate its angular velocity, and we come up with this number here. If I take and add the two kinetic energies and subtract it from how much we had, we still have a difference of 0.0516 joules. Okay, and so where did that energy go? Well, it probably went into doing work, because remember, if an object does work, it loses energy, or it transforms it into some other form. So what are some areas that the ball could have done work? Well, as the ball rolled down here, it's pushing against air resistance for that entire distance. Force times distance would be work. I don't think that's a real big form of energy or a large amount of work that was done. What I tend to think is that the ball was sliding down that ramp, and there was friction between the ball and the rails that the ball was doing work, and that friction would just be used to create some heat. And that's why our numbers aren't exact here. But this equation up here just needs to add some work that was done. Okay, and that's conservation of energy. It would have been a much simpler problem if I didn't have this ball on rails. If I just let that ball roll and where it's touching the ground is the same as its radius. So we'll just do that problem real quick again here. I won't explain maybe all the steps, but same things I did there. I cancel the mass. I'm going to factor out the velocity squared. The radiuses did cancel in this case. I'm going to get a common denominator. So 1/2 is 5/10, and 5/10, same thing as 7/10. And then I would multiply both sides by the reciprocal of that, and then take the square root, and that's how fast the ball really should be going if it didn't skid and slide here. And I guess maybe if we did it in a vacuum so there was no air resistance. But again, I don't think air resistance is a real big factor because it's not moving that fast. The faster it goes, the more air resistance there is. All right, so rotational kinetic energy. There are some buses, and it's a new form of energy storage that is kind of up and coming here, but we can take the big massive flywheel and rotate that thing very, very fast so it has angular momentum. And so we can tell from our right hand rule that it should be rotating this direction. That was my previous video. Okay. And if you use an electric motor or something to get that spinning really, really fast, you can store tons of kinetic energy in that rotating flywheel or gyroscope. Now, we have to think about what should the orientation of that flywheel be. Should it be rotating like this so that it has angular momentum pointing forward? Should it be rotating like this so it has angular momentum pointing up? Or should it be rotated like this so it has angular momentum pointing sideways? Well, the answer depends. Depends on what type of terrain the bus is likely to encounter. We do have to remember from our last video that the change in angular momentum is going to be in the same direction as the torque that was put on it. So if a bus is going around turns like this, and the bus makes a sharp left-handed turn, well, there'd be a torque on that whole flywheel like this. The front of the bus is turning left. Our right-hand rule says the torque would be in the up direction, and if this had a massive amount of angular momentum and we put a torque on it up, the angular momentum would change in the direction of up, which means this bus would likely do a wheelie when you're trying to turn to the left. Not good. Well, if it was in this orientation, we put a torque on it, that's in the same direction as the angular momentum, and that's all right. Just it'll get more angular momentum up. If the wheel was oriented like this and we made a left-hand turn, so we put a torque on it up, the angular momentum is going to change in the direction of the torque. Just trying to make a left-hand turn is going to lay that bus over on its side, and all of those are bad options for going through a road like this. But if the road was like this, where it was going up and down, the torque would be now in a different direction. So let's say that this bus is just cresting over the top of the hill and the front end of the bus is going to start to drop. I'm actually not going to give you the answer. I want you to predict what's going to happen if the front end of the bus is torqued downward. Hit pause and think about it. All right, now that you're back, and I'm not going to show you the answer, I just want you to think through it. But you can see there's issues with changing direction in this kind of bus. We can resolve all those issues if we just had a second flywheel spinning in the exact opposite direction. There would be no net angular momentum of the bus. And but still, if you put a torque on each individual wheel, it would require a massive amount of torque to do that. So it would be really rough on the housing of each individual flywheel, but the bus as a whole would not flip over. And there are actually buses that do this. This is an old bus from, I believe, the 1950s, and there's a flywheel right here in the center. And this doesn't have any motor other than that flywheel. It would have to stop periodically and use electricity to charge up that motor. But if you get the energy from the electricity from solar or wind or some renewable energy, it would be a very, very good use of energy for that bus. In fact, there's companies like Beacon Power that uses flywheel energy storage. They use this massive cylinder here. Actually, it's a ring. It's oriented vertically like this. They put it in a vacuum chamber so there's no air resistance. They use magnetic bearings so there's very, very little friction, and this thing can spin super, super fast with very little energy loss due to friction. And it's spinning so fast, actually it's spinning about Mach 2 is its tangential velocity, about 684 meters per second. It's going crazy fast. It has a mass of about 200 pounds of mass. LBM is pounds of mass, which is going to be about 90.9 kilograms of mass. And it has a radius. We'll find out here that it doesn't matter what the radius is. Because it was a ring, it was just mass times radius squared, not 2/5 or 1/2. This 1/2 was already there just because of the equation. So yeah, the radius, that gets squared and that gets squared, so the radius is going to cancel out there, which just turns out to be kinetic energy. So if I plug in the mass and how fast it's going, we get about 21,300,000 joules of energy that can be stored in this spinning ring. So solar energy works great when the sun is shining. Wind energy works great when the wind is blowing, but that energy can be used to spin these wheels faster using electric motors, and then you can pull off that energy when you need it. And there's massive arrays of these things already in existence. It's actually 100% recyclable, so there's no harsh chemicals like you would find in batteries and things. So a really, really neat energy storage device that is being implemented now. So a little bit more about rotational mechanics. Every translational equation has its rotational counterpart. So velocity, position, acceleration, kinetic energy, momentum, or impulse, changes in momentum. Every one of these translational concepts has its equal and counterpart in a rotational sense. That finishes up rotational mechanics.